In this video, we want to introduce you to the first law of thermodynamics. And the first law of thermodynamics is written down like this: delta E equals Q plus W. So what is delta E, right? So of course delta just means change in, and E int means the internal energy of my system. And what we mean by a system thermodynamically is typically a gas, okay? Now that's not restrictive. You can have liquids and solids when talking about thermodynamics, but specifically when we're going to be talking about the first law of thermodynamics, we're going to be restricting our conversation to a gas, and we're going to do different processes to that gas. And what those processes do is potentially raise or lower the amount of internal energy that the system has. Now, the internal energy is the energy that the system possesses inside, okay? So if I restrict my discussion to a canister of gas, and that canister has a piston, and the canister can also possibly be connected to a heat reservoir, could be a burner, could be a bath of ice to either lower or raise the temperature. I can do a range of different processes to this gas that will either raise the internal energy of my system or lower the internal energy of the system. And the internal energy is literally just the total amount of kinetic energy that the particles have as they're moving around inside the canister, as well as the potential energies that arise from their interactions. But assume that maybe I threw the canister and the canister itself gains kinetic energy. That kinetic energy that the canister itself has is not part of our calculation of the internal energy, nor is if I take the canister and I drop it or raise it up and I give it potential energy, nor is that potential energy of the canister as a whole descriptive in any way of the internal energy. So the internal energy is just the energy of the gas particles themselves as a result of being confined in the canister. Okay? Q is the amount of heat that we're either going to put into the system or take away from the system. Again, if I have a heat reservoir, say I have a vat of gas and I put it on a burner, then heat will transfer into the system if the canister is conductive. And if I put heat into the system, the average thermal energy of each individual molecule increases because their kinetic energy increases. So if their kinetic energy increases due to heat, then I will get an increase in the internal energy of the system. W is the work done on the gas. Okay, and we need to make sure that we specify work being done on the gas or work being done by the gas. So if my canister has a piston and I take that piston and I push it down, then if the canister or if the piston is being pushed down, then I'm going to increase the pressure inside the gas. And if I increase the pressure, then I have also increased the internal energy that the gas has. So if I do work on the gas, then I'm going to increase the internal energy. If I put heat into the system, I'm going to raise the internal energy. Likewise, let's say I take my piston and I pull it upward, right? If I pull my piston upward, then the gas has room to expand, and the average velocities of the particles will become a little bit smaller. And as a result of that, the internal energy of my system will decrease. And in that case, we would say that I've done a negative amount of work on the gas. Okay? Or if instead of a burner, we insert our canister into a bath of ice, then I'm going to extract heat from the system, and heat is going to escape from the gas into the ice reservoir, and Q would be negative, and in that case, that will also lower the internal energy of the system. So I can either add heat or extract heat. I can either do work on or a negative work on the gas, and depending on the combination of those things will dictate how the internal energy of the system behaves. Now, we need to talk about a couple of different things before we go on and actually do some math with calculations and so on and so forth. First things first, we need to define what we call a quasi-static and reversible and irreversible processes. Okay, so a quasi-static right? A quasi-static process is a process that occurs slowly enough that we would then say that the gas itself maintains a state of equilibrium, okay? And what we might mean by that is, let's say that I have a heat reservoir here, right? So heat is definitely going to move into the system, but if I let the heat move into the system slow enough, then I don't really get any sort of energy gradient between the molecules down here and the molecules up here, right? So as the heat is moving in, it's doing it slow enough that all of the molecules are essentially in thermal equilibrium with each other, okay? It's not like I immediately, put a flamethrower on the bottom of this and the bottom of the gas heats up really quickly, and so they start moving around very, very quickly while the gas molecules at the top are still cool, okay? That would be a system that is not in thermal equilibrium. So if we can cause our processes to occur slowly enough, then the entire system will maintain its equilibrium state, even if energy is being added to the system. And that's what we mean by a quasi-static process, okay? Another thing that we need to define are reversible and irreversible processes. Okay, so a reversible process is a process that I can exactly reverse the path of the process on what we call the PV diagram. So if I plot pressure versus volume for some thermodynamic process, right? Whatever its initial pressure and volume may be, we'll call this point A, and maybe we'll say that this is point B, right? And then maybe the gas takes a path like this. I don't care what the path is. So here we have low volume and high pressure, and here we have low pressure and large volume. So this would be the case of, say, taking a piston that's right here and pulling that piston up so that my pressure decreases as my volume increases. A reversible process means that whatever this state is here, I can exactly retrace the steps along the PV diagram, okay? And for quasi-static processes, I can do that, right? If my process is quasi-static, it is also going to be reversible. An irreversible process is one in which my path on the PV diagram can go from here to here, but I cannot reverse it. So again, let's say that I put a flamethrower underneath and I start right here, right? If I have a flamethrower, then it would actually probably be something like this, right? If I don't change my piston, then my volume is going to stay constant, but my pressure is going to increase. So this would be A and this would be B. And my path would look something like this. And for irreversible processes, I can't necessarily replicate my path the other way. And irreversible processes that don't meet the criteria of being in thermal equilibrium fall into this category. So irreversible processes don't allow me to retrace my steps. It's not like I can take all of the heat that I get from a flamethrower and extract it in exactly the same way that the flamethrower put it in. Okay. Now I can definitely do a reversible process that is at constant volume. That's not the issue. The issue is how the heat got into the system. Okay. And for an irreversible process, I cannot replicate that exact path. So these are some of the criteria that we're going to need to meet. A reversible process is what we're going to be focusing on as we move forward. Now we're going to look at several different types of processes: isothermal, isovolumic, isobaric, and adiabatic. And we're going to see how those different processes play into the first law of thermodynamics. And that's what we'll do in the next video. All right, we'll see you then.